In this video, we'll be looking at how we can approximate a car's speed at a specific moment in time. We're going to consider a car merging onto a highway. We'll use this picture of a car to represent the position of the car, and the distance from the picture's starting point will represent the distance the car has traveled. Watch the car moving along the road and see what you notice about the motion of the car. How fast do you think the car was moving when exactly 3 seconds had elapsed? Remember that if the car was traveling at a constant speed of 25 miles per hour, this would mean that changes in the car's distance, measured in miles, are 25 times as large as corresponding changes in time, measured in hours. However, at a particular moment in time, there is no change in time, so we can't measure the car's speed at a moment of time. We can only approximate that speed. To make this approximation, there are several measurable attributes of the car's motion we might be interested in. One of them is the number of seconds elapsed since the car began merging onto the highway. Another is the distance it has traveled since it began to merge onto the highway. I'll show the car's trip again. I'll use the length of a red bar to represent the elapsed time, and a blue arrow to illustrate the distance that the car has traveled. As you watch, think about how the length of the blue arrow, the amount of distance the car has traveled, is growing in comparison to the length of the red rectangle, the amount of time it has been traveling. We want to know how fast the car is moving at exactly 3 seconds after it began to merge onto the highway. To compare how the amount of distance traveled and the amount of elapsed time were growing, we can measure each of these quantities. I'll show how the amount of elapsed time increases again and mark off 1-second intervals to measure it. I'll also use arrows to show the amount of distance the car travels in each 1-second time interval. Each time interval has an amount of change in time, in this case 1 second. Also, each distance interval has an amount of change in distance. In this case, all of the distance intervals have different sizes. Now let's think about how these time intervals compare to their corresponding distance intervals. The black lines indicate how each distance interval corresponds to a time interval. So for each successive 1-second time interval, the size of each distance interval increases. Another way to say this is for any fixed amount of change in time, the corresponding changes in distance are increasing. And this is what it means for the car's speed to increase. Let's return to the question I asked at the beginning of the video. How can we approximate the speed of the car exactly 3 seconds after it began to merge onto the highway? Well, the general method is to use the average speed over an interval of time to approximate the instantaneous speed right at 3 seconds. To start, we can find the car's average speed over the interval right before the 3-second mark. Using this interval, we can find the average speed immediately before the 3-second mark as 3.87 meters per 1 second. This speed, 3.87 meters per second, is an approximation of the speed right at the 3-second mark. Then we can also find the average speed right after the 3-second mark. Using this interval, we can find the average speed immediately after the 3-second mark as 8.34 meters per 1 second. Since the car is speeding up, the speed of the car before the 3-second mark is less than the car's speed right at the 3-second mark. So the average speed over any interval of time before the 3-second mark must be less than the speed right at 3 seconds. This means that the first average speed is an underestimate of the instantaneous speed at 3 seconds. And by the same reasoning, the car's average speed after the 3-second mark is larger than the speed right at the 3-second mark. So the second average speed is an overestimate of the instantaneous speed right at 3 seconds. And this tells us that the car's speed right at the 3-second mark is some value between 3.87 meters per second and 8.34 meters per second. If we subtract these two approximations, then we can measure the precision of our approximation. Here, we know that we have approximated the instantaneous speed, right at 3 seconds, to within 4.47 meters per second of its actual value.